So let's crunch some numbers on this and see what it looks like. Okay, this is the sample that's on the handout on Blackboard. It doesn't actually tell us the value of XL, it tells us L and the frequency, so we can calculate for this. These are the same numbers that we used in the series RL circuit. So this 30.16 ohms was the same value for XL we had back in the series RL circuit, but things are going to work out much differently here. So the first thing to notice is that when we label the sides of the impedance triangle, we must show those as the inverse values, okay, here on the triangle. Now, when this was a series RL circuit, we had two nice clean numbers there. We calculated for the hypotenuse of our impedance triangle, and off we went, okay? We could do that. I could find out what these decimal place values are. The inverse of 10, this equals 0.1, I believe it does. And we could calculate this as well, and we could do that. But those numbers start to get ugly, and I think it's probably a lot easier to just avoid doing that and see if there are any other options here. Well, for starters, we were told that the power supply provided 120 volts. And that's fantastic in a parallel circuit. That means 120 volts is the voltage in every branch of our circuit. And 120 volts, we can use that anywhere in our calculations. So we are told that we have 120 volts. And we are told that the resistor, the resistive portion of the circuit, is 10 ohms. So that is just Ohm's law way back to the beginning. And that's one of the tricks to watch out for here. Sometimes we can't see the forest for the trees. We get almost overwhelmed by the amount of information. It's really important to try and just sit back, take a look, and apply the skills that you have. Because you possess all of the skills and all of the knowledge to make this work. You just need to recognize the opportunities. So what does current equal? I equals E over R. Okay, you learned that a very long time ago, and that's actually exactly where we're going to start solving this particular equation, okay, or this circuit rather. So E, 120 volts, divided by R, which is 10 ohms, okay, and we are absolutely using the value 10, not the inverse of 10, okay. Ohm's law means 10 ohms is exactly the resistance in the circuit, okay. We're now just doing math on the numbers in this branch. Okay, the fact that there are other parallel branches doesn't really factor into what we're trying to do and understand right here. There's 120 volts dropped across that 10 ohm resistor. Okay, awesome. What does that mean? It means that I equals 12 amps. Okay, so the current through the resistor, I subscript R, is 12 amps. Okay. That's what's happening right there. We have 120 volts, we have a 10 ohm resistor, that means there will be 12 amps flowing through it. Okay? Now we can go out here and we can do the same thing. There's 120 volts dropped across that load, and I know the impedance value of that load. It is 30.16 ohms. Okay? And so the same formula, we're just going to substitute. So this is actually I subscript R equals E over R. So if I said I subscript L, what does it equal? It equals E over XL. Same equation, right? We're just making sure we have all of the right variables so that we're talking about the same sides of the triangle or the same locations within the circuit so that we can apply Ohm's law. So still 120 volts. Now the value of impedance or resistance or reactance, so many different terms, 30.16 ohms, and that equals 3.98 amps. 3.98 amps. Okay, so now we can ignore the ugly, horrific impedance triangle with its nasty inverse values, and we can look at a current triangle, and we have the adjacent and we have the opposite. We're good to go. Okay, so we can use tan to calculate our angle is 18.31. Sorry, I probably threw that number out there too quickly. You might want to hit pause real quick as we go through this. Try to get the numbers yourself and then carry on and make sure that we're looking at the same numbers. So 18.31 is the angle, means 18.31 and 18.31. All of the angles are the same because these three triangles represent different variables of the same circuit, so they're all identical. Let's find IT. So we could use SOHCAHTOA with an angle and a side, or we could use Pythagoras with the two other sides to get our hypotenuse. Either way, we end up with an answer of, hit pause, do the math, come on back, IT equals 12.64 amps. Now here's where you want to pause. Every time you're doing the math, you always want to stop somewhere in about this neighborhood and say, do these numbers make sense? Let's look at what we have. Well, first of all, the hypotenuse is going to have to be the biggest number, right? And it is the biggest number. But look what we have. We have a number here, the adjacent, which is not a lot smaller, and then the opposite, which is quite a lot smaller. So what should we expect for an angle? A fairly small number, and that's exactly what we have. So I would suggest that at a glance, those numbers make sense to me. Okay? Now, let's go back and finish our impedance triangle, because we now know our current on our hypotenuse. So, how do we calculate impedance when we have current and voltage? Well, that's back to the old equation, R equals what? E over I. Right? Well, let's get the right variables in there. We're actually calculating for Z equals E over IT. Right? So 120 volts divided by 12.64 ohms equals 9.49 ohms. Are you okay with what I did? Are you happy? Are you really mad right now? That is definitely the value for Z. But I've got inverse of Z equals, so I better finish this off by saying inverse of. Now I kind of almost don't even care, to be honest with you, because we just finished the triangle. But I want to make the point that when you're filling in the tables and the exercise sheets, and when you're answering a question on the test that says what is the value of Z, it is 9.49. All right, but if you're answering the question, what is the value of the hypotenuse of the impedance triangle? Well, don't lose sight of the fact that that is the inverse of. Okay, so this particular equation, as I built the triangle, says what is the inverse of Z? Well, that would be the inverse of 9.49. Okay, hopefully I've stressed that enough. Like I say, just do it, get into the exercise sheets, a bit of repetition, get comfortable with what numbers go where and what's going on. Okay, but we didn't really do any math here. We didn't try to manipulate or understand this triangle. Right, we just filled in the blanks using Ohm's law, working one way and working back the other. Okay, notice also, sorry, I said I was done and now I'm not. Look at the numbers, 9.49 compared to 10 and 30. Okay, we know the hypotenuse has to be the longest side, but when you compare those three numbers, it's the smallest. Okay, which makes sense when we're talking about the circuit. Okay, and we can make it make sense in the triangle as long as we recognize the inverse. So, it's all working out. Okay, I've belabored that point enough. Let's move on. All we have to do now is fill in the power triangle. Okay, and power equals volts times amps. So, it's simply the voltage multiplied by the current of the adjacent and the voltage multiplied by the current of the opposite and the voltage multiplied by the current of the hypotenuse to find the opposite, the adjacent, and the hypotenuse of the power triangle. Hit pause. I'm going to fill in the numbers. 1440 watts goes there. 16.8 volt amps is the apparent power. And the reactive power is 123.9. 123.9 VARs. And finally, what is the power factor of our circuit? Well, it is the cos of 18.31 degrees, or it is 12 divided by 12.64, or it's 1440 divided by 1516.8, or, yeah, never mind. Power factor is, and it's going to be a pretty high number, right? It's going to be a good power factor. Nice small angle there. Our power factor is 0.949. And is it a leading or a lagging power factor? It is an inductive circuit, which means the current lags the voltage, making this a lagging power factor.